certain point, enough electricity flowing through your body, it's going to contract your muscles to where you can't actually control your muscles anymore. You can't actually let go. And so this is what brings in the importance of the GFCI breaker or GFCI device. Welcome, this is Stephen with Service Plus Electrical. We're on our second video here with David, with electrician Ed. We are talking about GFCIs. David has some diagrams and presentation. David, if you want to pull that back up again. In our first video, we talked about what is a ground fault. So that was a good starting point. We had some excellent diagrams of that, so hopefully you can visualize what a ground fault is. And in this video, we're going to be talking about what is the GFCI and how does it work. And so with that being said, David, where do you want to start on explaining what is a GFCI?
Okay, can you see what I've got up here?
Yep.
Okay, I think we kind of left off here where the our little friend was able to let go. And we'd mentioned that we don't want to depend on that because we may not be able to let go. So enter the ground fault circuit interrupter. This is a breaker, but it could also be another receptacle with GFCI protection built in, but it's all going to kind of work the same way.
So if I could, I'm going to circle back real quick, because on the last video we talked about when the unintentional path is created, if it has a nice path with low resistance back, then it would trip the breaker. When it's going through your body has enough resistance to it, and as well as the earth and whatever other paths take to get back, has enough resistance that not a lot of electricity flows, and so it's not going to trip a regular breaker. And you would say, well, when I get shocked, I just let go, and then I'm not being shocked anymore. Well, we covered that in the last video as well, that at a certain point, enough electricity flowing through your body, it's going to contract your muscles to where you can't actually control your muscles anymore. You can't actually let go. And so this is what brings in the importance of the GFCI breaker or GFCI device of whatever type it is. And so David's got a GFCI breaker on his diagram here. He's going to show you what this does.
Yeah, I'm going to show you. So it looks like a regular breaker. Some of them have these little pigtails. If you have a newer style, you may have what we know as what's known as a plug-on neutral, and they won't have the little pigtail thing, but you just snap it into that breaker. But if you do have a pigtail, you'll hook it into your neutral bar in the panel. And then we also need to break this little connection over here because this is now our return path that we're going to be sending back out to the transformer right there. And we need to bring that over to hook into this silver lug on your breaker. And then up here, your hot conductor, this would be kind of like still the bus bar where this is connected into. But this wire here would need to plug into the lug on your silver, or excuse me, your brass or copper looking screw, the darker colored screw on your breaker. And that's how you would hook that up in your panel.
And so normally the regular breaker only has the hot wire, the hot flowing through it, and the neutral just goes back to the source. But the GFCI breaker, it has both the hot and the neutral flowing through it, so it can then do its function, which we're going to describe here. How exactly does it work?
Yeah, so again, here's our potential coming down, heating up the hot side of this receptacle. So these screws here are connected internally to the smaller slot of your receptacle. And since it's on, your potential is coming all the way to this point again. So this is the same situation we had before in the last video, but when he makes contact, I kind of bring out in the article that there's actually slight delay, and it depends on the GFCI component in this thing, how long this is going to go through. And it also depends, before this trips off, the magnitude of how much is actually leaking through here. So there's a time curve and kind of a magnitude time curve that this tripping mechanism is based on. So we've still got the same ground fault going through here for probably just a millisecond or two. And again, it depends on how much. If it's 30 milliamps that's going through them, it's going to trip almost instantly within probably within 6,000ths of a second. If it's lower, like really lower, then this is allowed to take a little bit longer to trip off. But anyway, now it's tripped. And the way that these are made for protection of personnel, you probably wouldn't even have felt this, or you might have felt just a very tiny little tingle before this tripped off. Milliamps leaking out, bam, tripped off. Open the fault. Now we don't even have potential over here. You can't get shocked anymore. You could stand there and hold that forever. If you want to know what's inside this thing, this represents a circuit. This would be your hot side, and this is your little bridge device. This is where it would open, and this could be inside that breaker or inside GFCI receptacle. So here I'm showing a balanced circuit. There's 10 amps going through. And this is like a toroidal coil inside the GFCI where the wires are wrapped around it a certain number of turns. It comes out here and it goes through a load, and it's returning at the same time, same number of twists around this toroidal coil and going back 10 amps. That's a balanced circuit. And the way this works, the shape helps to kind of keep all the magnetic field, because when current goes through a wire, it creates a magnetic field around it. So this kind of helps to keep it concentrated in the middle, so it's not as affected by outside magnetic fields and things like that. This secondary coil, this is sort of like a transformer. So you've got your primary coil coming in, going out, and it's got current going through it. This secondary coil will pick up on any magnetic field that is generated here by these two. And if there's an imbalance, let me explain what I mean by that. I said that there's a magnetic field created in a conductor, but in this little area here, it sees this magnetic field and it sees this one in the opposite direction. These two would oppose one another, and so this magnetic field would just almost completely disappear. And therefore, no current would be induced into this secondary coil here. And let's say that there's a ground fault out here. You touch something. There's going to be current that is induced into this because the magnetic field would be imbalanced here.
So in your balanced drawing here, most likely that's indicating that the intentional path is being taken, right? So all of the
Yes.
electricity going through the hot wire is coming back on the neutral wire. So that's an intentional path. And there is one scenario where you could still be getting shocked if you happen to be in series with those two. Very, very unlikely scenario, but that is important that people understand that. You still want to be careful what you're touching.
Yeah, if you came up and grabbed a hold of this receptacle, and most homeowners are not going to have that opportunity because they keep covers on it and they've got, safety precautions in place. It'd probably be more like an electrician that thought the circuit was off and we grab a hold of something. And because we're, Stephen, I think that it could still trip if you're standing on the ground because you're on a grounded surface. Some of that would bleed down through you. Hopefully, hopefully it'd be
Yeah.
enough to offset this and trip, but you may still
So
get shocked.
so this drawing is showing that everything's balanced so that under 99% of scenarios, everything flowing through that hot wire is going through whatever you plugged in and back in through the neutral wire. So everything's equal. And then I'm assuming the next picture is going to show what happens when it's unbalanced.
Yeah, okay. In this picture, we've got this is showing an imbalance uh, circuit here. You've got 10 amps going out. It's going through the hot side of this blender motor, juicer motor. And as far as this is concerned, everything is fine. It's got 10 amps coming in, it's got 10 amps going out. And here we've got somebody that's found this weak spot in the cord. Maybe this got slammed in the steak knives drawer. Nobody noticed it until he came along and touched it. We've got a little bit of current bleeding off, and it's about 6 amps that's going through him, or excuse me, 6 milliamps that's going through his body.
And
He
the
may
rest
not,
is going back through the regular path.
the rest is taking the rest, the normal path. So this, it could be more than this. It just depends on how he could be standing in a puddle of water with bare feet on concrete. And then he's probably going to make a really good path. And he might feel that. But in this case, it's just 6 milliamps. It's almost the same amount here that's going back, but not quite. There is a little bit of current that's being induced into this sensing coil. It's connected to the relay. And in this situation, this is what's happening right before it trips, because we talked about that magnitude time curve.
And so that 6 milliamps, that's enough to trip a GFCI.
Yeah, a Class A GFCI will trip. And a Class A GFCI should trip between 4 and 6 milliamps is what it's supposed to do. There are other GFPE devices that protect equipment, and they may trip up to like 30 milliamps. But in our homes, Class A circuits, from what Class A GFCIs are normally what we install. It'd be a special situation where you would install something else. But
and so how much does it, a lot of people are familiar with the amps because the breaker is labeled with amps, but how many amps does it take to actually kill someone?
oh, now I don't remember my exact numbers. If the heart goes into fibrillation, there is a point that happens. First, Charles Dalziel's experiment showed that there was a mild tingling. That was one stage. And then as you increase the current, it became painful. You would want to let go. Most people are going to want to let go. If you can hold on a little longer through the pain, your muscles actually begin to, it jumps into the nervous system and it causes your muscles to contract. and you get to that point where you can't let go voluntarily. You'd have to be pulled apart. And sometimes we're saved from electrocution because we fall and the weight of our bodies rips our grip loose.
Mm-hmm.
You
But
don't want to wait.
we're talking in the order of milliamps, and so this is, I'm sure it's somewhere under, I know it's somewhere under 100 milliamps, so we're talking less than a tenth of an amp.
Mm-hmm.
Less than a tenth of an amp is enough that you will not be able to let go, and then the oscillation of the electricity interrupts the oscillation of your heartbeat, essentially.
Oh yeah, that's another point I hadn't really thought about bringing up, but with alternating current, it takes a lot less electricity to hurt us than, let's say, direct current. Oh, and also you could have alternating current, but a much higher frequency than what we normally have in our homes.
Mm-hmm.
Um, and it wouldn't hurt you as bad. It's like, have you ever dinged a crystal glass or just a glass and you can hear it vibrate? If you rub it with water, you can get it to sing to you, real
Mm-hmm.
high pitched voice, whistling sound. That's vibrating at a certain frequency. And it just so happens that the electricity that we have in our homes is 60 hertz. That means it's going back and forth, alternating back and forth at 60 cycles per second, which means it's changing directions 120 times per cycle, excuse me,
Mm-hmm.
per second. That just happens to be about where the human body sings and
Mm-hmm.
whistles. We vibrated that. So it's really kind of a dangerous situation. It could be, if you're in another country, it could be 50 hertz, but it's still pretty close to the same thing. It's gonna hurt you. So you can take a lot less of alternating current at 60 hertz than you can with direct current.
Yeah, and to come back to this diagram and back to the topic, I must interject that this drawing is a great example why you should make your wife untangle the vacuum cord. Because my wife, like, she likes to wad it up and then just hang it on the vacuum.
Okay.
And then when there's a knot, you just jerk on it. But no, you actually have to untangle the knots and wind it up nice and neat, because otherwise you get the sheathing of the cord gets broken and then you can get shocked like this.
Yeah. Yeah, and things wear out too. Or I think I think we drop a lot of things, like a hair dryer. I'm thinking of if you drop something enough times, it may look like it's still good and it may still run, but there may have been something that broke loose inside. And even if you've got a plastic um, thing that you're holding on to, if it's got metal screws in it or something, you could still get shocked unexpectedly. So
And
there's
so
just little,
there's many little scenarios that can cause you to get shocked, and back to the beginning of this, the regular breaker isn't going to trip on most of those scenarios.
yeah. And so in this case, we've shown that it's opened. I'm still showing that there was an imbalance, but actually once it opens, it's going to be zeroed out like that.
Mm-hmm.
And once you've stopped it, now you've got electricity stopped right here, potential, nothing flowing anymore.
Excellent. That's what we need. So we're not getting shocked anymore, right?
Yep.
All right. So
So
now if you're sticking with us, you know what the ground fault is. You know not only what a GFCI is, but also you know how it works. And so in the next video, we're going to say, what does a homeowner need to know and what do they need to do in order to ensure that these GFCIs are doing their job. So see us on the third video, and we're going to talk about what the homeowner needs to know about GFCIs, what you need to do. And thank you. We'll see you on the next one.
thank you, Stephen.